Hi everyone, my name is Michelle Quan. I am a rising sophomore here at the University of Minnesota, double majoring in chemical engineering and material science. My project is titled Automated Quantitative Analysis of Silica Nanorod Dimensions via Watershed Segmentation. And my mentors are graduate student Christopher Neal and Dr. Michelle Calabrese, both within the chemical engineering and material science department here at the U. Within the Calabrese group, our work can range over many different topics, but my work specifically focuses on silica nanorods. Nanorods are our focus because they are anisotropic, meaning that they're asymmetric in nature. They're shaped more so like a test tube, so one end is flat and the other end is rounded. This allows us to have some directionality, which is why we focus so heavily on nanorods and their anisotropy. However, silica nanorods are diamagnetic, meaning that they have low magnetic susceptibility. Previous literature has successfully doped silica nanoshells with paramagnetic materials like iron, which means that it's potentially possible for us to dope nanorods with iron and therefore control their directionality based on a magnetic field. However, in the varying synthesis processes we're trying to explore, the size analysis of nanorods is the key challenge. Literature typically measures nanorod dimensions by hand using a program called ImageJ. You would be measuring about 30 to 60 nanorods per image, and this is quite time-consuming over multiple images. Therefore, our ultimate motivation is to automate this process and design an algorithm to efficiently measure silica nanorod dimensions. The entire program was created in MATLAB, and this figure 1 demonstrates 6 key points along the way. Image A shows a typical SEM image, and SEM stands for Scanning Electron Microscopy, where a beam of electrons is shot at a sample and the signals given off by that sample result in the image. You'll notice that there is a section that makes up the particles and the images, and there's the bottom section that makes up the date and the scale bar, among other things. We care primarily about the scale bar within this bottom section. So we end up splitting the image on this line here and measure the scale bar separately to set scale for the rest of the program. From there, we move on to image B. In image B, the key difference is that we've made the image into a binary image instead of an RGB image. And you'll notice there are still white clouds of pixels here and there that do not result from the nanorods themselves. This noise is typically coming from scratches in the plate that you can see here. We wish to eliminate this noise in order to have the program focus solely on the nanorod dimensions themselves. So between images B and C, we eliminate the noise, and we also apply a distance transformation. Image C demonstrates this. The basic concept of a distance transformation is to measure the distance from every pixel to the nearest pixel of interest. In our case, the pixels of interest are the nanorods themselves. The nanorods here in image C end up being black because they have a distance of 0 because they are the pixels of interest. Whereas all of the other pixels have a non-zero integer and have shown up as white. Following the distance transformation, we move on to image D, which is a watershed transformation. This watershed term is coming from geographical literature where there's a watershed, a raised area between catchment basins, like two lakes. In our case, the catchment basins are the nanorods, and the raised areas are any place around the edges that are not the nanorods themselves. This is how we do segmentation. Additionally, image D is with RGB labeling to make it slightly easier to find where the nanorods are. While it is still difficult, you may notice that there are some discrepancies here that match up with nanorods here in image E. Because image D is so difficult to look at, we apply the watershed segmentation image and overlay it onto a cleared binary image, demonstrated here in image E. However, you may notice there are striations within the nanorod body. These striations are the product of oversegmentation, a common problem occurring in most literature on watershed segmentation. To address this issue, we redo the distance transformation and also the watershed segmentation. However, we add thresholding to reduce the impact of these striations and ensure that they don't show up in the final product. The final product is in image F. You can see the particles with RGB labeling once more, but they are also surrounded by boxes. These boxes are called oriented boxes, and they are the minimum area bounding box that completely encloses each of the nanorods. When done correctly, the bounding box length should be equal to the length of the nanorod, and the width of the bounding box should be equal to the diameter of the nanorod. Now that we can see how the program works step by step, we can compare it to results tabulated manually. Manual analysis was conducted with ImageJ. I did 3 trials of measurements for both length and diameter and averaged all of that data, and then compared that to the data obtained automatically. As we can see in figures 2 and 3, the automatic data in both length and diameter tends to have lower average values than the manually obtained data. To determine whether or not this difference was statistically significant, we ran a t-test and found that at the 95% confidence level, there was no statistically significant difference in average length. However, the difference for average diameter was statistically significant. One component that could have caused the statistically significant difference is an issue of overlap. You may have noticed that the image we tested earlier had minimal overlap, and that's because we chose images that avoided heavy overlap in order to test just the basic functionality. Overlap confounded the ability of the program to properly segment. When comparing figures 4 and 5, we can see that with minimal overlap, the segmentation does a relatively good job. However, with figure 5, there's much more overlap. And here there's both over-segmentation of nanorods, but it's also missing nanorods in the background. This could be due to the shadows of the foreground nanorods, obstructing the ability for the computer to segment out background nanorods. Future work should explore limiting the impact of overlap and avoiding these issues. Ways to eliminate this overlap issue can fall into 2 categories. The first is lab-based sample preparation techniques. To prepare a sample, we have our sample of nanorods and we dilute it with a solvent like ethanol. From there, we drop cast that onto a sample plate, allow it to evaporate, and then put it into the SEM. We could use more alcohol to create more dilute samples with lower concentrations of nanorods per droplet. In addition, we could use more volatile solvents to decrease the evaporation time. The other area of interest with mitigating the overlap issue is to explore other segmentation techniques aside from watershed segmentation. While watershed segmentation was chosen because it has an ability to segment the edges quite well, it doesn't do so well with overlap. A different segmentation technique called contour segmentation has been demonstrated to work for overlapping nanoparticles that are not nanorods. They're more so spherical. However, this should be explored in the future. In its current form, this project and the corresponding program serve more so as a proof of concept to demonstrate the viability of automated programs to help us in our measurement process. And under optimal conditions with minimal overlap, we can still get a decent estimation of both length and diameter of a nanorod population. This will help accelerate our analysis process when we change other synthesis processes, and hopefully help us identify trends. This will contribute towards our future work in iron doping of silicon nanorods, in addition to the creation of hollow nanorods. In closing, I would like to quickly acknowledge the Multicultural Summer Research Opportunities Program, funded through the Office of Undergraduate Research, for funding this program. Additionally, I'd like to thank Heidi Fanning and Vicki Monroe for running this program despite all of the unprecedented circumstances we are under. Finally, I would like to thank my mentors, Christopher Neal and Dr. Michelle Calabrese, for their continued support throughout the program. If there are any questions about my project, I'd be happy to answer them now.
Yeah, I've got a quick question. You mentioned that the width measurements were a little bit higher in discrepancy between manual sampling and your computer program. I was wondering,
yes,
could that be due to the fact that you're using the what did you call them, the boxes, the least fit boxes or something like that?
Yes.
There's maybe more variation along the length of the nanorod in terms of its width than there is in the width, since you're only sampling, less cross-sectional area?
Yeah, so in the paper I addressed this, but within this sample it's a little bit harder to tell, but for some of the particles like this, they have a varying width with a wider part and tapering in at the point, which is a more irregular shape. But because of this, the nanorod may not lay completely parallel to the box and may run at a diagonal. Because of this, all of the lengths and the widths would be almost like the hypotenuse of various right triangles that you could make within the rectangle, resulting in the automatic data being smaller than the data you could obtain manually. So this issue may be bigger in width.
Cool, thanks.
Michelle, that's very nice work. I have a, I was going to say stupid question, but how about a poorly informed question? If you're doping iron in, could you use a magnetic field to get the nanorods to lay kind of unidirectionally, and would that help your sizing, your program to accurately determine them?
I hadn't actually considered that. However, you are right in that we hope that when we dope the nanorods with iron, we would be able to use a magnetic field to orient them all along the same axes. So that could help in segmentation. I haven't explored that yet because we haven't doped any, but that's a good thing to explore.
Thanks.
Do we have any other questions for Michelle? Well, thank you very much. Very well done. We're going to take a little bit of a break right now. If anyone has any questions for any of our presenters so far, feel free to share with them either in the chat or here. And then our next presentation will be Chen at 11:25. So feel free to get some coffee or whatever. But great job so far. I'm so proud of everyone.
Really nice job there, Michelle. Thank you.
Thank you.
Though I did miss the markers.
Yeah, unfortunately, I was worried my screen would be a little too small to have both markers and the PowerPoint up.
Nah, it's fine. I'm just joking. It was great.
Michelle, what would you use these nanorods for?
Some literature has attempted to put these nanorods within a polymer matrix, and therefore it could act as an altering of the properties. Like if we dope them with iron, it could provide a better, and we orient them all in one direction, it can provide a better path for conductivity in heat or electricity. So it has great applications in terms of smart materials and finely tuned composites.
Wow, great.